All right. You guys ready? No? Thank you. All right. Let me get started with a word of prayer. Dear Heavenly Father, we thank you again for this day. I thank you for the students. Just ask that you bless our work today. Again, just pray that we'd understand a little bit more about rotations and moments of inertia, torque, and all these things. And just pray that the students be encouraged to work on their homework and just do their best, Lord, each day for your glory. In your name I pray, Lord Jesus. Amen. So I just have a little bit more to talk about from last time before we go on. So I will try to do that once I get my laser properly energized. Any questions before I start talking? All right. So last time I talked about, the moment of inertia, how to calculate it. And we worked out a few, right? And ultimately, I talked a little bit about this derivation. Just to run through it again briefly. If you think about a rigid, so this is like a rigid body, right? If it's rotating, you can calculate the position at a given little mass dm as the sum of the distance to the center of mass and then plus the distance from the center of mass to that little bit of mass you're trying to calculate the kinetic energy for, right? And if you break down the r prime, there's two pieces, right? There's the piece which is parallel to the axis, and there's the piece which is perpendicular to the axis. The piece that's perpendicular to the axis has to do with the spinning, right? The piece which is parallel has nothing to do with the spinning. And if this object is fixed in place, then this n is constant. That's what it means for it to be a rigid body. It's stuck like that. And so when you calculate the relative velocity, relative to the center of mass, that is, then the n piece drops out. You get dr dt like this. And then after about a page of calculations, some things drop out, and we get to the theorem that the net kinetic energy for such a rotating rigid body is equal to the kinetic energy of the center of mass for the system plus the kinetic energy of the rotational piece. The kinetic energy for the center of mass is 1/2 the total mass of the rigid body times the velocity of the center of mass squared. The velocity, the kinetic energy for the rotational aspect of the motion is given by this down here, 1/2 I omega squared. All right, so just a quick review. That's what's going on there. So it's interesting, of course, to calculate the moment of inertia for different bodies, and we showed how to do that for some things last time. Let's see here. I talked about this example. The thing I didn't talk about yet, though, is the parallel axis theorem, which is it's important if you find yourself needing to calculate the moment of inertia for an object. All right, so well, first of all, there's a standard list of known formulas for moment of inertia, right? We've derived some of these, and so I have a handout for today. So on this handout, on the front page, there is this, like some pretty typical moments of inertia for different things, and every moment of inertia. So if there's more for your row, then pass it behind you. So I'll let you guys take care of this side. Just pass it back there. So, all of these example moments of inertia are with respect to some rotation axis. So as you look at this, you'll notice that each object, there's some kind of axis of rotation indicated. Once you get your hands on it, notice, like, for example, the slender rod axis through the center is one case. Oh, I got more. Oh, you guys got it? Everybody have the attendance sheet already? Oh, so we'll start back here and let it work its way. All right. Anyway, my point to you is all of these different moments of inertia for various bodies, there's a given axis, right? So what if instead of rotating the axis around the one you're given, you're rotating the object around another axis which is parallel to that axis? Well, the good news is there's something called the parallel axis theorem, which says that you can calculate the moment of inertia for that same body with respect to a parallel axis just by this simple formula. And so here's the formula. The moment of inertia with respect to an axis parallel to the given center of mass, the moment of inertia through the center of mass, plus the mass times the distance between the axes squared. Well, that's the moment of inertia around the non-center of mass axis. And here's a derivation of it. Basically, just calculate the kinetic energy in two different ways and can compare, and then you see that the moment of inertia for the new axis is given by the moment of inertia through the center of mass and plus this mh squared term. Anyway, so, and then you can also, if you don't have the moment of inertia through this, so this is special. There's only one center of mass for an object, right? So some of the things on your sheet are not centers of mass rotation, I think. Are these all center mass? Let's see here. How about this one? Part D, thin rectangular plate, axis along the edge. Would that be the center of mass? No, the center of mass axis would be, well, there's a few, right? There's the one that cuts through the middle of it and is parallel to it. That would be center of mass axis. You could also take the axis which is perpendicular to this the center of the rectangle. That would be a center of mass axis. The point is what is a center of mass axis? It is, shockingly, an axis which goes through the center of mass. So if you have this shape, there's kind of, here's a natural center of mass axis. But you could also do this one, right? Or you could do this one. There's a few natural choices. All right, anyway, the point is, if you want to compare the moment of inertia, where'd it go? Stupid thing. Just a second here. I didn't want to go page down. I just wanted to scroll down. Here we go. So the formula, if you want to go from one axis to another, you do the moment of inertia from the original axis plus the mass times the distance squared, the difference of the distance squared, where these are the distance from the new axis relative to the center of mass. So this is the parallel axis theorem when you're switching from one axis to another and neither of them happen to be a center of mass axis. So it's a little bit more complicated, but that's how you do it. All right. Anyway, I may not have even given you guys a homework problem about these, but I feel like I'm supposed to tell you these things. So here we go. An application of this would be the barbell problem. So if we talk about a barbell, an honest-to-goodness barbell where we have, like bowling balls at the end, and I'm neglecting, well, it's not really an honest-to-goodness barbell, is it? Because I'm neglecting the mass of the rod, all right? So in this case, what's the moment of inertia? Well, I would calculate, let's see here, the center of mass axis, right? Let's see here, so what I do, moment of inertia for the first one plus the moment of inertia for the other one. How do I figure out what is the moment of inertia for the barbell? Well, let's see here. So what's the center of mass for the barbell? It goes right like that, right? How far is that from the axis we're considering? Well, it's L over 2, all right? So I do m times L over 2 plus the moment of inertia through the center of mass of the barbell, which is 2/5 mr squared. We worked that out. Well, I didn't work it out, but I explained to you how you could do the integral to do it last time by looking at dividing the sphere up into cylindrical shells and doing the calculation. And so when you work this out, you get this as your moment of inertia for this barbell. So sometimes you need the parallel axis theorem to account for your mass not being rotated around its center of mass, but being displaced and rotating around that like a displaced axis. All right. All right. Anyway, so that was pretty much all I had to say about that. I'll put it away. Now, if you look at the back side of the handout I gave you, here's the calculation that I got stuck on last time because I didn't realize it was this complicated. So Simon was right. It was the sine of the angle. It wasn't sine. I think I had sine squared. I'm remembering that from the I think the vector area element or whatever. But anyway, here's the actual calculation for why the moment of inertia for a spherical shell is 2/3 mr squared. So, whew, it's hot in here, isn't it? It feels hot to me. I should start wearing shorts on days like this. I don't know. I don't think that's allowed for faculty, though. Are shorts allowed for students?
Oh, yes.
I heard a resounding yes. Stand up for your rights. What? No. It's okay.
They're just really.
Huh.
So half of them are invisible.
Let's see here. I've taught for Liberty about, I don't know. I forget how many years. 11, 12, something like that. I'm still waiting on my first reporting of dress code violation. So I've not yet met a student that I really felt like I needed to report one on. So, to be clear, I have seen many dress code violations that I felt like I should have reported, but at the same time, I'm left with the question of, should I actually do that? Well, no, because I don't know the student, number one, and number two, I don't even know where to start. So, to be clear, I don't care if you wear shorts in here. All right. So, what's that?
That's tough.
That's what?
Sorry.
That's what?
I digress.
Oh. You want me to crack down on the short wearing in here? Is that what I'm hearing?
Yes.
So okay. I mean, I saw a seafall worker like midriff bearing. Like what? Really? Come on. That seems not right. Anyway, I guess I'm from a bygone era. But anyway. So here I'm into lecture 27. This is the lecture 27 PDF I'm going to get into here. So I have explained to you guys a little bit. Basically, let me just recap here. We have that, omega is d theta dt, right? Alpha is d omega dt, which is d squared theta dt squared, right? So we have angular velocity, angular acceleration, right? And I've also explained to you a little bit that the kinetic energy rotational is equal to what? 1/2 the moment of inertia times omega squared. So this is rotational kinetic energy. So everything we've done so far, though, has just been descriptive of rotational motion, right? I haven't yet explained to you what's called dynamics. What's dynamics? What's the difference between kinematics and dynamics? Do you guys know? So really, we're doing rotational dynamics. So what we want to describe now is why. Why is there a rotational? Why is there a rotation? What's causing the rotation, right? And so the answer to that is there's got to be some force, right? So let's just think about, you've got a mass, right? And we're talking about it with respect to some, axis of rotation, yeah? So we can measure the angle theta like this. And there's some force on this mass that's causing it to rotate. What kind of force would make it rotate? Like, if I was to take a force, right, and put the force like, oh, I don't know, like this, right? What part of that force would cause a rotation? Not all of it, right? Like, to be most dramatic, what if I made the force directly outward like this? If the force was purely radial from the center of rotation, right, there'd be no rotation at all, right? That wouldn't cause a rotational motion, right? So really the part of the force which matters is the part which is perpendicular to the radial arm. All right, so we call that the tangential force. So that's like this guy. Sorry, I'm trying to decompose this force here. So this is the tangential part of the force, right? There's this other piece, which is the radial part. So only the tangential part is really going to give you the rotational motion, right? And so what do we have? We have the tangential force is equal to what? The mass times what? Times the tangential acceleration. But what is tangential acceleration as it relates to the radius and the angular acceleration? Do you guys remember? So if this distance here is r, right? Then what is a sub t? A sub t, remember, is mr alpha, right? And then what? Well, then, inspired by our experience over here, remember what we had, among other things? The moment of inertia for a point mass was what? It was mr squared, right? This is the moment of inertia for a point mass. So if we want to see that in this, well, I should do what? I should just multiply by r squared, right? So if I do r times the tangential force, we get mr squared alpha, right? Okay, and so on the right hand side rather, now what do we have? We have I alpha, where I is the moment of inertia. And on the left-hand side, we have something new, all right? On the left-hand side, we have what's called the torque. We use a tau for torque. So torque is equal to, I alpha. How is torque defined here? I'm defining it at the moment as a scalar, all right? And how does it work? So rotation, in some sense, is one-dimensional. In the sense that we can describe rotational motion with a single angle, right? And the convention we have is that if the axis for the rotation, if you take your hand and you grip the rotation axis, put your thumb in the right hand in the direction of the rotation axis, then your fingers curl in the positive sense of angle. So the rule for this is that torque greater than 0 implies counterclockwise motion, right? And the torque being less than 0 implies clockwise motion. Does this terminology resonate with you guys? I know we don't really have clocks anymore, but imagine yourself in a world where a university put clocks in classrooms that you could look at, right? It's too great an expense for liberty, I think, but we repaint the room every year, but we can't spend $10 on like a clock, I want clocks in my rooms. Sorry, I digress. We used to put them up sometimes, but I think people got tired of bringing their own clocks and putting it in. Anyway, any questions? So, let's see here. Let me give you an example. My example, let's see here. Oh, so if I, interestingly, a lot of times you might want to talk about the angle here. And typically we measure the angle of F off the radial axis. So if this angle was, let's say, theta, what would Ft be? It would be what? It would be F times the sine of theta, right? Just by the way, okay? Notice that this angle and that angle are the same. That may not be immediately obvious, but it's like, let's see here. Well, wait a minute, is that true? That's not true. That theta's got nothing to do with that theta. I better change this to something else. Let's call it phi. Okay, my bad. Sorry about that. Anyway, example 1. So I'm going to skip past my example 2 is interesting, but let's start with something easier. Let's go to example 3 in my notes. So you've got, here we go, a pulley. And on one side you've got mass 1. And on the other side you've got mass 2, all right? And we're still going to assume that the rope is essentially massless, all right? But this time we're going to assume that the pulley actually has mass. So the pulley has mass big M and radius R. Assume rope does not slip. All right? And what we'd like to do is to try to write down the rotational analog of Newton's second law, right? So that's what this is. This torque equals to I alpha is the rotational analog for Newton's second law. So I just derived it for a single mass, but the way this works is if we have a system, we have to calculate the net torque if there's more than one force involved, right? So what's making, so let's think about the pulley, all right? So what we want to do is the net torque on pulley, right, is equal to the moment of inertia for the pulley times what? Times the angular acceleration, right? So what is the net torque on the, why is the pulley turning? What's going on here? Think about it. There's two things, right? You've got this force right here, right? And you've got that force right there. What force, what am I talking about? I'm talking about M1G, right? And over here I'm talking about what? M2G. Well, actually, I'm not sure I entirely believe that. Why? Yeah.
Because there's no angle.
No angle?
No angle.
Well, the angle we would be thinking about is, you know, like track a particular point on the pulley, like maybe this one, right? And you can measure angle like here. Sorry, my picture too small. Like it's the rotation of the pulley that we're thinking about the angle for. That's the alpha. I'm talking about the rotation of the pulley. The thing I'm a little bit sketchy about here is it true that the force that is transmitted by the rope to the pulley is just M1G? I mean, it's the tension, right? It's the tension that pulls on that. And I'm not entirely, is that right? Let's see here. So like, how do we figure out what the tension is? Let's think through this for a second here. I'm not entirely convinced. So if I go down here to this mass, right? I've got what? I've got T1 that way, and I've got M1G down there. And what do I have? I have M1 times the acceleration is equal to, you know, M1G minus T1. All right, so if I wanted to simplify this, discussion for the sake of us getting started on something less complicated, what I could do would be to assume that the acceleration was 0, right? Like describe what's going on right when it's balanced, right? But anyway, let me keep going on here. So this is M1A. That's just Newton's second law on M1. On M2, what do you got? You have T2 going up. You've got M2G going down. What do we got? We've got M2A equals to what? Now notice that if this is positive direction for A, right? If that's the same A, I guess that's the question. Is it the same A? I think it has to be the same A on both sides. Otherwise, the rope would be stretching, right? Yeah. So on this side, the T2 is positive, and it's minus M2G, all right? So I'm stuck with that, okay? Now, there's a relation between A and alpha. What is it? So if the rope is not slipping, what's the relation between the linear acceleration of the masses and the rotational acceleration of the pulley? The relation is this. A is equal to R alpha. Now, technically, I should be careful. It could be plus or minus, right? I'm assuming, let's assume for the sake of specificity, let's assume that M1 is greater than M2, all right? So that the motion's actually this way, all right? So that the acceleration is making M1 drop, okay? In that case, that makes, well, then I'm defining, then I would be defining clockwise as positive rotation, right? I mean, you can do that. Just be aware that's what we're doing, right? We have to face these issues. You know, what is the positive sense of rotation versus how have I defined A to be positive? You know, we have to wrestle with whether or not those match up. Anyway, so we have that. So for this example, I'm saying alpha clockwise is positive. If I wanted to fix that, I'd have to go back to my Newton's equations and instead define M2 dropping to be a positive acceleration. Then I would also have that counterclockwise was a positive direction. If I want to, because if once I write A equals to R alpha, that links the translational motion of the masses to the rotational motion of the pulley. All right. So then what? So what is actually the net torque on the pulley? What do we have here? Well, it's the tensions, right? Tension 1 and tension 2. So what's the torque from tension 1? So I have, what is the moment of inertia from the pulley is what? It is 1/2 mass of the pulley times R squared alpha equals to what? So my default, guys, is to make counterclockwise rotations positive and clockwise rotations negative, right? But annoyingly, I made a choice, and that choice has consequences, right? The choice of making M dropping a positive acceleration, that put me in the world of thinking of clockwise as being a positive rotation, right? So I have to count clockwise torques as positive torques, right? So, okay, why did I put 1/2 mR squared here? I'm assuming the pulley is what? It's like a cylinder, all right? So that was said in the more complete statement of the example in my notes, all right? So we're assuming the pulley is like just a simple cylinder. Anyway, so what's the torque from, so the torque from R1, so the question is, how far is that? Let me draw the picture bigger. So here's a picture of the pulley, right? Tension 1's like this, right? So what's this distance? This distance is R, the radius of the pulley. So that gives us a torque of RT1. See, because tension 1 is causing a clockwise rotation, right? So that's positive, RT1. On the other hand, T2, opposite story, right? We have minus RT2. Now what can you do with this equation? So this is what you're up against. To describe the motion, you have to solve this system of 3 equations and 3 unknowns. Right. What I have in the notes assumes the acceleration is 0, I think. So, well, I don't know. I don't believe what's in the notes, actually. So, anyway. Maybe it works out the same. I don't know. Let's see here. So, if I divide this by r, what happens? You divide this by r, what do you get for the third equation? You get what? You get 1/2 m. What is r alpha? R alpha is equal to a, right? So I get 1/2 ma is equal to what? Looks like T1 minus T2. So you see, if you divide the torque equation by the radius, you get back to something with the same units as the Newton's laws, and then you can combine these equations reasonably and solve them. So, do you guys want me to solve them, or can we go on? I think it's good for us to go on, so do that. Let's see if I can find an easier example. Example 2. So suppose you apply 100 newtons to a wrench. All right. What's the maximum torque you can place on a rusty bolt? By the way, I have not forgotten about your extra credit problem and or the special relativity quiz. I've not gotten to them. I'm still in the middle of a Calculus 2 test I'm grading, and I will eventually get through that and transmit all of the great news to my Calculus 2 class. Then I'll be back to the stuff in here I need to grade. But I've not forgotten. It is not lost. It is not forgotten. It's just I'm behind. So what do you guys think? Is this even a meaningful question? So how does this go? Something like this, right? You got a bolt. I can't draw bolts. Anyway, here's a bolt, right? And you've got this wrench. And then Mr. Top Hat is pulling down on it with all of his might, right? And you're trying to twist this bolt, right? You're trying to cause a rotational motion like that, right? So what would the torque be produced if he was pulling down with F naught here? What's the torque produced if he's pulling directly down perpendicular to the radial arm? What's the torque produced? Yeah? Right, yeah, so whatever this distance is, right? So if we call that distance d, the torque is equal to d times F naught, right? So what's the max torque? It's as big as, you find a longer wrench, you can get a bigger torque, right? So this is like why if you pay attention to people with big trucks, they don't try to loosen the nuts on the hubs to the trucks with a little wrench, right? They've got a 6-foot one that they can, mess with the end of it, because you can multiply the force essentially by having a longer arm, right? So the force multiplier. And it almost seems like you get something for nothing, but what's the rub here? By the way, what are the units for torque? So what are the units for torque? So we're looking at distance is in meters, right? F is not is in newtons. It's a newton meter. Newton meter is also known as what? It's a joule, right? So torque has the units of energy. So a larger torque is a larger energy. So that means by having a longer, radial arm, you can create energy, right? It seems kind of like a professional motion machine, doesn't it? If you want to have 10 times the energy, you just have 10 times longer the arm. What's the rub? Like, why is this not a something for nothing kind of deal? What's the resolution? Yep.
For the longer wrench, you have to travel a longer distance.
Exactly. That's exactly it. For the longer wrench, you have to apply the force over a proportionally longer distance, and that's why it's all energy is conserved. So yeah, you get a larger force, but you have to apply that F naught over a longer distance to produce that same torque. All right. So there's that. You can ask fun questions like, what if you want to, let's see here. My example 5 in this notes, I have the question of how long a lever do you need to increase your applied force by 100 times? And so here we're thinking about like a seesaw kind of deal. So you've got like a pivot point, all right? And you've got some lever, right? You're applying the force like here. Here's your output force. And here's your input force. If you want the output force to be 100 times the input, what's the situation you need? So suppose you want that to be 100 times the input force. How would you achieve that? So the idea here is that at the pivot point, the torque should be 0, all right? And so that means what? So if we look at this point right here, the sum of the torques is equal to 0, but that's on the one hand, whatever this is, let's say L1, let's call this thing L2, right? So you have L1 times Fin minus L2. Actually, is it minus L2? Let me see here. I think they're both, as I have it pictured, I think that should be plus L2, F out. Here we're getting into sort of like questions about your conventions for one-dimensional motion. Sometimes people write minuses, sometimes people don't. So people might disagree on these equations, depending on how you want to do the conventions. But if I'm sticking with the convention that counterclockwise, oh man, what have I done? What kind of motion is that if this is the, so it seems like I keep doing clockwise positive today. What's wrong with me? Well, fine. I'll fix it this way. I'll make this go that way. There we go. There we go. Now I have counterclockwise motion. All right, positive. Great. Fine. So I'm saying that this is 100 times Fn, so what does that tell me? L1 Fn plus 100 times L2 Fn so as I give that, I guess that force is L1 plus 100 L2, right? Times Fn to be equal to 0, which tells me what? Let me not be an idiot here. So simple principle. So the torque here is 0, right? So what we want is L2 times F out to be balanced, right, by L1 times F in. But I've also said that F out is 100 times F in, right? Sorry, I was a victim to my conventions in terms of plus minus, and I don't have enough time here to sort through whatever stupid thing I was doing. So F in, we cancel them, right? What do we get? L1 has to be equal to 100 times L2. So I think it depends. The way the question was asked, I end up saying that you need a lever 101 times as long as you place the pivot point, if that makes sense. So if L1 is 100 times L2, I need the proportion to be 1 and then 100 more, right? So if your pivot point, is 1 centimeter from the place where you're applying the force, then you need another 100 centimeters over here to get this multiplication by 100 times. So you need a 1.01 meter wrench to achieve this. But it totally depends on how close the pivot point is to where you're applying the force, right? And so like in practice, how does that happen? Well, it kind of depends on what we're talking about, right? What's a practical pivot point? You need something solid that you can, apply the wrench on. They won't move. All right, enough about wrenches. Let's see here. So let me go back to the example I skipped, actually, because it's an interesting one. So I hope you're not getting lost in my quibbling over conventions here. The big story is just this: to calculate rotational motion, we need to figure out the net torque on the system and set it equal to the moment of inertia times the angular acceleration. That's pretty much it. So an interesting and really different problem we haven't really even thought about before is this. Suppose you have a solid cylinder, all right? You have a solid cylinder, and on that solid cylinder, you put a little mass like up here. So solid cylinder, mass big M, and then I have a little mass M that I'm attaching to the rim of the cylinder, all right? This is rolling on a plane without slipping. What happens? Right? Can we describe the motion? What is Newton's rotational second law here? How's that go? So what I want to do is I'm going to think about the rotation relative to the center of the system here. So I'm going to basically set up, measure the angle to here like theta. All right? So if that mass is not there, does anything happen? Like if I just, put, if I had a solid cylinder sitting around here somewhere, I was going to steal your water bottle, but it's useless to me. You and your fancy square bottle, useless. Ah, that'll work. So, all right, watch the rotational motion. You guys ready? So nothing happens, right? Because there's no torque on the system. But in this situation, there's a torque, right? Because this mass, what makes the torque? Gravity, right? So if we think about gravity there, it pulls directly down, right? Like this. I'll draw it big. How do you get the part of the gravity which is tangential? So we want the tangential part of gravity would be like this, right? And then of course there's this piece down here that we don't care about so much because it would be radial if I made my picture right. All right. So what's this here? What's this angle right here? Follow me. The angle that's complementary in where theta is pictured is up here. And that angle is also complementary to the red angle that I'm trying to figure out. In other words, the red angle is theta. Theta is also this angle right here, which means that the tangential piece is mg cosine theta. So that would be the tangential force, right? So what's the torque? The torque, in this case, would just be minus the radius times mg cosine theta. That is the torque that little mass being on the edge of the cylinder would create on the system. Does that make sense? Why did I put a minus? Yeah. Clockwise, right? Yeah. Finally, I'm thinking clockwise is positive for finally. Yep.
Is torque a vector or scalar?
Yes. Depends on the context. So I would say torque is a vector. Next class probably. Torque will become this. Torque will become the radius cross the force applied. So that's what we do next class. And there, the direction of the torque will be actually in the direction of the axis of rotation which it creates. But for our purposes here, we're thinking of it one-dimensionally. So it's not strictly speaking, it's not a magnitude, right? Because it could be positive or negative depending on whether we're thinking of clockwise or counterclockwise. So it's, in this context, maybe the best thing to say is it's a one-dimensional vector. It's like that. But that's a good question. I think generically speaking, vector for sure. Just like angular velocity is generically speaking a vector, but it's a scalar over there. Okay, so what's the moment of inertia for this system? See, this is supposed to be equal to I alpha, right? What is I? There's two pieces. So moment of inertias are additive. So here, what you've got is, well, you've got 1/2 mr squared. That's the moment of inertia for the cylinder. All right, we derived that last time. And plus, you also have the moment of inertia for just the point mass on the rim. That's easier. That's plus little m r squared. So big M, I'll put feet on it. Little m, no feet. And alpha, what is alpha? Well, alpha is d squared theta dt squared. So there you go. This is the rotational Newton's law for this problem. Now, you can test some cases, right? Does it make sense? What happens when theta is like 90 degrees? That would be the case that the mass is up here, right? What's the torque? 0. That makes sense, right? On the other hand, when theta is 0, the torque is just RMG because gravity is directly torquing it, right? When theta is 180 degrees, you've got minus a minus, you get a plus, right? Because over there, when it's on the other side, the torque is actually counterclockwise according to our conventions. Check this out. If we let theta equal to, let's say, beta minus 90 degrees, well, let's say pi over 2 because we do radians, right? With the calculus, we do radians. Then here we could look at what's cosine of theta in that context. Well, you have cosine of beta minus pi over 2, right? So in this context, this is just sine of beta. All right? And if beta is small, this is approximately beta. And in this context, we have the following. We have minus r mg beta equals to 1/2 m r squared plus little m r squared beta double dot. And you can solve this and rewrite it as beta double dot plus, let me cheat for a second here. Oh man. Two mg, I'm just doing algebra here, 2mg divided by big M plus 2 times little m r beta equals to 0. This right here is the simple harmonic oscillator problem. It's the same equation we get as for a spring. All right? This right here plays the role of k. That's like a spring constant for this problem. The solution to this is beta of time t is equal to beta naught cosine of omega t, let's say. That's a solution for this. And here omega is the square root of 2mg divided by big M plus 2 little m g. And so that actually, you could say, this is, by the way, equal to 2 pi over the period. You could solve that for big T, and that would give you the period with which this like coffee can with like a bolt attached to it, solid wheel of cheese, a giant wheel of cheese with a bowling ball on its edge. The period with which it would rock back and forth if the mass was pretty close to down here. All right, so this is describing the period of this rolling back and forth, provided your motion is kind of close to minus 90 degrees. This is an example of the theory of small oscillations, which is in like a big topic for like higher level mechanics. And it's also, of course, interesting to engineers because, well, you guys want to understand how things rotate and, oscillate about. But anyway, I think we're done for today. So.